When we think about cybersecurity, we usually imagine these super complex, multi-stage hacks, right? But what if I told you that sometimes the most devastating vulnerability is actually really, really simple? That's exactly what we're diving into today. We're going to break down a flaw in a tool that millions of developers use every single day, a bug that left the door wide open for stealing a company's biggest secrets. And to kick things off, let's just look at what that blind spot was worth.
Yeah, this wasn't just some what-if scenario. This one, single flaw, it earned a bug bounty hunter a cool $11,850. I mean, that's a serious chunk of change. It really tells you just how big of a deal this vulnerability was.
So, you got to be asking, right? How can one tiny little mistake be worth that much money? Well, to figure that out, we need to look at what makes a perfect digital heist. We're not talking about smashing down the door here. This is about the thief who just walks right in, pretending to be someone you trust.
All right, let's get into it. First up, we're going to look at that core vulnerability, the $11,000 blind spot that made this whole thing possible in the first place.
Okay, so to really get this, you need to know the two main characters in our story. First, you've got GitLab. Think of it like a super secure bank vault. It's where companies store all their most sensitive secrets, the CI/CD variables they need to build and ship their software. And then there's the GitLab runner. The runner is like the armored truck driver, the trusted messenger, whose whole job is to go to the vault, pick up those secrets, and safely deliver them where they need to go.
And here's where it all goes wrong. The problem was, well, it was basically an identity crisis. When a messenger showed up at the vault to pick up the goods, the vault just didn't check its ID. Seriously, it just trusted any program that said it was an official GitLab runner. It handed over the keys to the entire kingdom, no questions asked.
So you can see the problem, right? This creates this huge, dangerous opening for what you might call an evil twin attack. An attacker could build their own version of the runner, one that looks and acts exactly like the real deal, but with a secret mission to make a copy of every single secret it touches and send it straight back to them.
Okay, so how would an attacker actually pull this off? How do you build one of these malicious messengers? You might be surprised to hear that it's actually pretty easy.
Really, it's just a simple four-step recipe. First, the attacker just downloads the official source code, which is totally public. Second, they inject a little bit of spy code, a tiny function that's built to do one thing: grab secrets. Third, they tell that function to phone home, send all that juicy data back to a server they control. And finally, they just compile the whole thing into a brand new program that looks identical to the real one. And when you actually look at the code, it's amazing how targeted this is. The attacker only has to change one single file, the Docker executor. All they do is add one malicious function. They even gave it a pretty obvious name: send variables. And its job? Simple. Grab all the variables, wrap them up, and ship them out. It's basically like putting a digital wiretap right in the heart of the whole operation. All right, so building the tool is one thing, but that's only half the fight, right? A Trojan horse is completely useless if you can't get it inside the gates. And that's where social engineering comes into play. You have to trick someone, a developer, a sysadmin, into actually using your fake tool instead of the official one.
And an attacker has a ton of ways to do this. They could, say, publish a Docker image with a name that's almost identical to the real one, just hoping for a typo. Or they could write these super helpful-looking blog posts and tutorials that sneakily link to their poison version. They could even go on developer forums and spam links claiming, hey, my version fixes this common bug. It's all about exploiting the natural trust that exists in the dev community.
Okay, so let's play this out. The attacker's plan works. The Trojan horse is inside the walls. Now we get to the fun part. For them, anyway. The payoff. What happens when an attacker gets a hold of these secrets? What can they actually do? This is where things get really scary.
Look, we're not talking about some low-level user passwords here. These are the crown jewels. We're talking about the keys to the entire kingdom. Credentials for cloud providers like GCP and Azure. Access tokens for Kubernetes clusters that run everything. These are literally the master keys that give an attacker complete control.
And once they have those keys, an attacker's power is just massive. They're not just watching anymore. They can actively start messing with your code, creating new branches, injecting malicious stuff. They can use the stolen tokens to approve their own changes, completely skipping any security reviews. They can even hijack the deployment pipeline to push their malicious code straight to production, right where your customers can see it. It's like they become a super user developer with God mode enabled.
Yeah, it's a terrifying thought. But thankfully, this story has a good ending. GitLab patched this vulnerability. So let's take a look at how they fixed it, how they secured the vault, and, maybe even more importantly, what we can all learn from this whole thing.
And the fix was just as simple and elegant as the vulnerability was. GitLab just implemented that ID check we were talking about. Now, before the vault gives away any secrets, it checks the digital signature, the SHA hash of the runner that's asking. It takes that signature and compares it to a list of official trusted ones. If there's no match, no secrets. The fake messenger gets stopped cold at the door.
You know, this whole thing is a perfect example of a really important cybersecurity idea called the trust boundary. A trust boundary is basically that invisible line where a system decides, okay, I'm done verifying, now I'm just going to trust. And the big lesson here was that the runner program, our messenger, had to be considered outside that boundary. You can't just take its word for it. It has to prove who it is before you let it in.
And this brings us to a final, really critical takeaway, which the researchers behind this put perfectly. They said containerization is not a confidentiality control once secrets legitimately reach the workload. What does that mean? Well, a lot of us think that if our code is running in a container, it's automatically safe. But that's not true. Once you've already given your secrets to malicious code, it doesn't matter if it's in a container or not. The container can't save you then. The damage is already done.
So, that leaves us all with one big question we should probably be asking about our own work. Think about it. From our cloud providers to our build tools, even our own team members, everything and everyone in our development pipeline touches secrets. So the question is, do you really know who they are? And have you checked their ID?